So another question I got from this Ask the Professor session was about what about tramway? And tramway, we have another rail, we have the groove rail, and there you have a lot more wear than we have in the heavy rail, like we have on the passenger trains, and you get more RCF. So how to catch this problem also in this question? And the question was, what kind of hard steel we need of tram rail or in the wheels to get rid of the wear? So you could also say, when you have a wheel with a flange, then you get a lot of flange contact. So that means when the wheel is going over a sharp curve, and that's what we have in tramway because it's always in the city, and then we have always a problem to make this curve. And therefore you get a lot of wear in this side of the flange, and also on the side, on the gauge side of your wheel. And how to get rid of that? Yeah, you could say, okay, make it easy and just make it harder. But harder means that you could get some RCF stresses inside the steel, also in the wheel and in the rail, and therefore you can get some cracks. So it's always a balance. What is the best choice? And the best choice is, yeah, what do you like? It's always a compromise. Do you like wear? So you have to welding again and repair welding to repair the gauge corner, or turning off the wheels more rapidly or more frequently? Or do you like a harder rail and wheel? And then you get more problems of cracks in your wheel and on your rail. So it's always a devil's solution. What do you like? One of the students asked us, what is the right hardness of wheel or the rail? And is that the right combination? And what is the right recipe to get this in a good balance? So I asked this question to Professor Zilili, so as my colleague. So please, Zilli, could you explain a little bit more to the students what is really the problem in this wheel-rail interface?
Okay, then we have here a test rig made of real rail material and real wheel material. And here we can test, say, the wear or RCF of the wheels or the rails. And what we consider here is that, for instance, the wear of rail, it is determined by the stress and also then the microslip. And then this wear, if it wears a lot, then it separates the initiating cracks of RCF. So in this sense, the wear is benign. On the other hand then, of course we don't want too much wear.
That's the other side.
Yeah, this is the other side. So there is always a balance between how much wear you want, but not too much, and just enough to separate the RCF. This is for the rail side. And the same for the wheel side. And then there is also an interplay between the different hardness of wheel and the rail. And how to take all this into consideration then, in the past, people are doing this by trial and error, and that is usually quite expensive because then you make a lot of error or mistakes. So this is why we have here now the test rig to try to have some kind of generic model which can be used on later by the railways to find the optimal match of the hardness of the wheel and the rail and the right profile of wheel and the rail to minimize the costs caused by wear and RCF of wheels and rails. I hope this helps a little bit to you to go further with wheel-rail interface.
I think it's very good. Thank you, Zilli, for this answer. When I make a conclusion of this, I think I can say we are looking for the magic wear rate and how to find it. And I think that's exactly what you said.
Yes.
It's more or less how to find it in your system, in your wheel-rail system, in your own country or your company. How to find this real magic wear rate. And that's it all about. And that's because of trial and error, as I said, that we also have models. We do the test over here, so then it is a little easier and a smaller window to choose out what is the best recipe, best practices, whatever. But even there, is always finding the right balance.
Precisely.
Okay, thanks. So another question I got this week was about resilient elastic rail pads. First of all, I'd like to explain what is really a rail pad. I have here a sleeper, a wooden sleeper, the old-fashioned way in Holland. And what we like to show you is what happens with a real rail pad under the rail and in the connection between the sleeper. So this one is just new. It's brand new, it's elastic and also a little damping material inside. And that's the special one we use in Holland. So we have different types and also hard or softer. So it's a lot of, in all the world you could say, about what kind of elastic polymers or whatever you need as a rail pad. But when we put this one in, and after 5 years using it in the track, it looks like this. You can see it is totally worn away. Everything is almost burning away, and that's really the case. It is really burning away, and it is getting thinner and thinner till you don't have any material left anymore. So that's really happening inside. So you can imagine that when you see this as a new one and the old one, is really an important part of your rail system, inclusive the operations of trains running over it. So it is really reduction of the stresses and also the energy you put in when a train is rolling over, and this energy is going inside this pad and it will more or less burn away because he is absorbing this energy. So when you talk about switches, then we have to see what kind of materials or pads, rail pads we need. So as you could see that we have already in Delft University, we did a good research on what is the right rail pads or other damping materials you need inside the rail, between the connection between the rail and the sleeper, and also underneath the sleeper, like in the sleeper pads. We have a fully optimized design, and the question was, I can read it, is TU Delft currently engaged in or preparing to replicate this simulation in a field test? And the answer is yes, we did, and also with success. But the problem is how to implement it in the world, but also in Holland in a wider scale. And that's because of innovation needs to be proven technology because of safety. So the question is, in our laboratory where we are standing here, we test it, it works, although the modeling says it's good, but now the next phase is how to bring this in practice, and it must be proved to technology. So we have field tests, we do it, and that at the end it will be implemented. Another question was, do other countries already use this? And the answer is yes, yes they are. And especially England, Switzerland and Austria, they're using this specific rail pads already in their switches. Hopefully this will give an insight how it works and what we are doing here in the university. Thank you. Another question I got this session was about defects and heat affected zone. I think it's really interesting to understand more about this phenomenon to get defects in your rail. So you need welds. You cannot get rid of welds because we cannot make one big long rail, so you have to need the use of welds. And you get, therefore, you put heat inside the rail, and therefore you get a softer session on the rail, and that's the heat effector zone, and that implements, that you get some more problems in defects. But the question is, what is this heat effector zone? And I think here we are standing at a certain turnout switch with the frog, and I have here a weld in front of me with some problems like we have like the squats. So I can point to you what does this look like. So when you have here, for example, this small indentation because of the wear part, so the softer rail will wear away, and we have here in between just the welding itself. It's harder, and just before and after the weld you get this cupping, and you get a good view what that happens and what it do with the steel, and that's you say you get the squats. So the question was, what about a flash butt weld? Is that better? Is that a better choice? And what about this heat effector zone? And is that the same or less or more? So please tell me more about it. I think it's a nice question because a thermal weld has a very wide heat effector zone, and when you go for this flash butt weld, it's much smaller. So that means that the wheel, when it is turning over,
is really rolling over this heat effector zone instead of sinking in. So when you have a wide heat effector zone, the wheel is just sinking in this soft steel, and therefore it's bumping against this welded part, and that's much harder. And then you get a really high impact of force, and then you get the squat. So the mechanism is clear. So the smaller the heat effector zone is, what you have, for example, with flash split welding, the better it is, so that it will take much more time before you get the same defects like squats as when you have a thermal weld. So the answer is yes, it is much better, but still it is a heat effector zone. It's changed different characteristics of the material, so you get at the end always some defects. You cannot help it.